engineering conversation and innovation. This is Schulich Connects, proudly sponsored by TD Insurance.
So it's great to welcome you here today for this month's Schulich Connects, nature-inspired engineering solutions for a sustainable and regenerative future. And this event is proudly sponsored by TD Insurance. The University of Calgary, located at the heart of southern Alberta, both acknowledges and pays tribute to the traditional territories of the people of Treaty 7, which include the Blackfoot Confederacy, comprising of the Siksika, Piikani, and Kainai First Nations, the Tsuut'ina First Nation, and the Stoney Nakoda, including the Chiniki, Bearspaw, and Goodstoney First Nations. The City of Calgary is also home to Métis Nation of Alberta, Districts 5 and 6. Engineers solve problems. Engineers look for solutions to make things better. And a big part of that is thinking of where to turn, how to generate ideas and how to generate solutions. And we often tend to get a little complicated in how we're trying to find these solutions. And the panel today focuses on looking to nature to find solutions for the problems that we're trying to solve or the opportunities that we're trying to unlock. And if we think about it, nature has had thousands, if not hundreds of thousands of years to try to come up with ways to address things that we're doing right now. So our panel today will weigh in on the history of biomimicry, how it is used, and where innovation could take us in the years to come. In terms of some logistics for our event, because we're quite happy that this is both an in-person as well as virtual event, for our in-person guests, please hold your questions, and a mic runner, one of our staff members, will come and give you the opportunity to ask your questions after the panelists have had some introductory remarks and questions from our moderator. And for our virtual guests, please email your questions to ssemc@ucalgary.ca, and one of our staff members will ask the panel those questions in due course. So I'd now like to take a moment to introduce you to our moderator, Dr. Marianne Egermont, who is a professor here in the Schulich School of Engineering and also the Associate Dean of Sustainability. Dr. Egermont is a Biomimicry Institute Fellow and has been working in the field since 2004. She edits and designs, you're going to pronounce it for me?
Oh, Zygote Quarterly, and there's a QR code on the table which will take you right there.
Which is an online bio-inspired design journal and has won numerous awards in her field. Dr. Egermont has also served on the board of the American Society of Engineering Educators, ASEE, from 2004 to 2017, and was recently inducted into their Hall of Fame. I'd now like to pass it over to Marianne, who will introduce today's panel and get things going. Thank you.
Great. Thank you, Bill. Thank you for the introduction, and thank you all for joining us this morning. As Bill mentioned, I've been working in the space of bio-inspired design or nature-inspired design for the past 20 years, with probably over 8,000 or 9,000 students. So a lot of students have been exposed to this material. And we've even been able to take them to one of the NASA labs, which is looking at bio-inspired design. So I took a whole bunch of students to NASA Glen, which is in Cleveland, where they got to tour the labs and talk about how NASA is working on nature-inspired solutions for both our planet and for space exploration. So what NASA is doing is looking at extreme organisms on our planet to figure out how they operate and kind of abstract, right, design principles from those operating conditions and apply them to their research. We've always been inspired by nature. I don't think that's a surprise. In the year 100 BC, a Greek engineer, we would call him now, designed one of the first robots, which was a dove, and he was trying to make something fly, right? So inspired by nature. In the year 1000, one of the first people to try and fly jumped off a building with wings strapped to his arms. This was somebody who was working in a monastery, so a monk. Anyways, he broke both his legs, so that didn't work, but he survived. The Wright brothers, as we know, were looking at underlying principles, right? So not let's strap on wings, but how does this actually work, and how can we learn from the underlying principles and make something fly? So that's what we do in the classes. We look for biological strategies. How does an organism achieve a certain function, and how do we abstract that for engineering? And that's resulted in some interesting work from our students. So the question is, right, can we start looking more at biological strategies? We are in desperate need of sustainable solutions for the issues that face us today. Biology can teach us a lot, right? When we go to a zoo, I always find that they're telling us about the organism, not what we can learn from the organism, right? There's so many lessons to learn, which is why making sure biodiversity persists and we keep all that information available, because we will need this to survive, is my firm belief. So can we move from the Anthropocene to the Biocene, which is what the NASA conferences are calling themselves these days. So with that, I would like to introduce our first panelist and give her a moment to speak. We have Linda Celine to my left, an associate senior interior designer at Stantec. Linda has built a wealth of professional experience across multiple market sectors, including justice, recreation, post-secondary, hospitality, and healthcare. And one of Linda's key attributes includes the ability to assess client needs and design creative and appropriate spaces. She's passionate about creating environments promoting and sustaining healthy work, play, and living experiences, and is enthusiastic about applying biophilic, so our love for nature, and biomimicry principles in her work. So please welcome Linda, and I'll invite her to say a few words.
Good morning, everyone. Thank you. I am just thrilled to be here. Marianne saw me do a talk at Buildex, well, pre-COVID, and I fell in love with the field of biomimicry a little bit ago. And it was I was in the Joshua Tree Forest out in Nevada, and I was walking with a naturalist there, and he was showing me this crust of the earth. And it was all these filters, these bacteria straws. And I remember thinking, man, wouldn't that make great insulation? And that started the process. And then I was at an event for carpet. And one of our heroes of biomimicry is Janine Benyus. I'm sure a lot of us know her. If you don't, make sure you Google her. And Janine has just been one of the forefront big thinkers of biomimicry. And I was sitting beside her at dinner. It was my luckiest day ever. And we were talking about solutions, and I was thinking about pine cones, and how some particular pine cones survive fire, and they need fire to activate the seeds. And we just got into this great conversation, which led me down the road of really thinking how biomimicry can be used in my field with design and architecture. How can we simply use less and look at nature to use less? Nature does not soil itself. It's a full circle. Everything gets used, gets repurposed, and it comes right back. So that's my passion for biomimicry, and look forward to hearing more and talking more. Thank you.
Fantastic. Thank you, Linda. Next, we have Jim Gilliland, who's Director of Engineering Services at Williams Engineering Canada. Jim's been involved in the building design industry for more than 25 years. His passion is to support communities by helping develop sustainable and resilient infrastructure that will address immediate needs while being part of a community's long-term vision. Jim has worked to find cost-effective solutions that support the local economy, suit the local environments, address the effects of climate change, and make the community more resilient to extreme environmental events. He deeply values the friendships he's developed while working on projects in First Nation communities, and with Frog Lake First Nations in particular. Please welcome Jim, and Jim, over to you.
Well, thanks very much. Yeah, super great to be back in person again. And in the buildings industry, I guess, why would biomimicry be of interest to buildings engineers? And to me, it's a lot of this very similar themes that have already been spoken about. It's fundamentally, nature is extremely good at optimizing resources, using energy effectively to sustain itself and in an optimized way. And as buildings engineers, Williams Engineering, and my particular passion is to try to look at buildings in a similar way, almost like an organism. It's a building is actually a set of integrated systems that interact with each other and impact each other. And so biomimicry is definitely an opportunity for buildings to be much more optimized rather than being in a siloed sort of environment that we've been over the last, well, traditionally, where each component is designed in isolation. So the industry is changing, and we need to look at the integration of all of these different systems, like the building envelope with the mechanical system, with the lighting system, and look at how all these things impact each other to create an optimized system. We also need to look at what buildings do to our environment. When we build them, it creates an impact on our environment, and we need to look at what we're doing to the environment, and ultimately we can design buildings to counteract those effects and ultimately even make a positive contribution to the environment instead of always destroying it. So that's my particular passion in this area.
Great, thank you very much, Jim. Last but not least, we have Dr. Eric Limmeker, who just joined the Department of Mechanical and Manufacturing Engineering as an assistant professor. Dr. Limmeker is a specialist in unsteady aerodynamics with industry experience in mechanical design. In 2013, Eric returned to grad school to study the aerodynamics of rotating and accelerating wings with a focus on biomimetic design and renewable energy applications. And since obtaining his PhD, he has sought to combine his academic and industry experience working on wind turbine theory and design principles for low-head water turbines. Please welcome Eric. And Eric, over to you.
All right. Thank you, Marianne. I suppose with that intro, I'll talk a little bit about how I got into biomimicry in general. So my master's degree, I was looking at Samara seeds, which is this particular class of tree seed that rotates spontaneously as it falls. And there's a very interesting flow pattern that generates. And so we were interested in looking at how we can generate the same sort of patterns and to what beneficial effect, because this pattern happens to generate extra lift. So looking from that biomimetic perspective, it is managing to stay aloft longer and generate extra lift that we didn't know how to do in the sort of conventional aerodynamic design that we do. And so that interest has sort of continued. That was just my master's. And I continue to be interested in how we can look to nature, how its two key goals of maximizing efficiency and also a competing goal really being resilience, of how does it respond to changes in the environment in a very organic way. So I suppose I'll leave it at that to start out.
Fantastic. And I had a conversation with an engineer last night at the Engineering Student Society dinner of past presidents, and he was complaining about Samara seeds in his gutter. And I said, well, what you don't know, and I told him Eric's story. And he left feeling much happier about the Samara seeds. So, I take these stories to other places. So I have a few questions for our panel, and then once people start waving at me from the back, we will hand it over to questions from the floor and from online. So I'd like to start off. I'm going to go in reverse order, so be ready, Eric. I'm going to start with you. Can you provide some examples of biomimicry at work and maybe your sort of favorite application possibly?
Sure. So again, my area being aerodynamics, and you brought up flight in your intro, that might be the longest standing attempt at biomimicry that humans have been involved in. We saw birds and we said, oh, I want to do that somehow. Now, in conventional flight, obviously that is in some very simple sense biomimetic, that we've looked at how do we generate lift with stationary wings. Another area that I myself continue to be interested in is now, as we go to smaller and smaller scales, how are birds managing to fly without just straight wings, but looking at very unsteady, very sudden maneuvers, and how are they taking advantage of those underlying physics? So I would say one key application that I'm interested in would be bird-inspired drones. So looking at how are they taking advantage of many different degrees of freedom, many different motions to respond to the disturbances in their environment there. So that would be one.
All right. Jim?
Excuse me. There's a really great example actually right here on campus at the McKimmie Library rebuild or modernization, or renewal, I should say. The exterior envelope of that building, and I'm not sure who's aware of the design of that, but it's a double skin, double envelope, and the exterior skin opens the windows on that, open and close depending on which direction the sun is coming from, and that allows air to circulate and rise as it heats up, and it ultimately remove the heat from the building without having to provide any mechanical input to provide those that cooling. So that's a great example. It's sort of a fundamental basic example that's it's very mechanical, because there's a sensor that says, okay, the sun is shining on the side of the building, and therefore the temperature is above a certain threshold, so we're going to open the window. It would be really great if we could come up with a system that actually doesn't require any mechanical input or controls, that we really just rely on nature or natural phenomena. I was reading an article just last night in preparation for today about how you could use the thermal expansion of steel, or as a cladding system, to actually expand and ultimately warp and create a gap that would actually accomplish the same thing without any sensors or any sort of input whatsoever. And that's, to me, that sounds like a really great idea.
Mm-hmm. Fantastic. Linda?
Yeah, there's immense amount of research going on, but I'll give you the example of paint. A peacock has no pigments within its feathers, but when we look at a peacock, it's just brilliance, right? The refraction and the density of color. And we're tracking now so many people researching how we can apply a surface to a wall or to our cars, all of that, anything that we want to see a color on, and we're only using the refraction of light alone, not all the harmful chemicals that we see in our world today that can go into paint. So that's one example of many that we're seeing. It's very promising.
Yeah, the whole area of structural films, right, and structural surfaces is expanding a lot, right? So lots of hydrophobic, hydrophilic surfaces where you print microstructures rather than applying chemicals, right? So structural kind of forms to solve some issues. If you look at a shark versus, say, a sea turtle, right? A shark is very smooth. Sea turtles have all sorts of algae buildup and all sorts of stuff. Turns out the denticles on the shark skin, so their dermal denticles on the exterior of the shark skin, don't allow for that buildup, which has inspired a film that is an anti-fouling surface that can be applied to the hulls of ships, so they don't come out of the water as often for cleaning. But an even smaller kind of nanostructure has been used by a company called Sharklet Technologies, and that's an antibacterial film. It turns out bacteria also do not like to create large colonies on these structural films. And we were able to look at that with a biomedical student who's doing a capstone project, who did an experiment, and because he said, okay, let's prove this to to Schulich at least. And so we tried to get bacteria to grow on this film, and it was almost impossible. So that has great possibilities for antimicrobial, antibacterial surfaces, say in hospitals, right, where superbug generation tends to happen. So some really interesting work being done in nanostructures inspired by nature.
Can I add to that? Because
Yeah.
can you imagine if we could have a film on our windows and our cars that there wasn't dirt, and we are not using fresh treated water to wash our vehicles? So
Yep.
yeah, that's exciting.
Yeah, there is a paint in Germany. I'm sure you can get it here too, but local conditions are important. So there is a paint, an exterior paint called Lotusan, which is based on the surface of a lotus leaf, which also has those nanopillars. It makes the building self-cleaning, but you do need rain on occasion, right? So in a super dry area, that's not useful, but for areas where it rains a lot, right, this is something that saves cleaning crews and soaps and all sorts of other things that wouldn't drain right into our environment. So going to our next question. This question is a big one. How is biomimicry used to solve some of our real world problems? Eric, do you want to give us your thoughts on that?
Sure. Perhaps I can start with another example, or I can start from the general principle as well. Again, we're looking at the competing challenges that nature is always trying to solve, the two key ones being, as I said before, efficiency and resilience, so responding to changes in the environment. So another application that is particularly fascinating to me would be for wind turbines, looking at acoustic noise generation. So something that some of you may have seen in certain articles is looking at blade design and how we modify blade design to solve that noise generation problem, which of course, from the perspective of trying to expand renewable energy into greater areas and take over a larger portion of our energy generation, it's important that it's not having those negative consequences on nearby communities. So noise generation is a concern. So if we can find ways to take inspiration from birds once again, about how their wings manage to suppress noise generation. So you can imagine an owl that's going out to hunt. It has that goal of minimizing its noise. And the design of the trailing edge of its wings actually tends to do that. And so there have been some attempts to look at blade designs that maybe have serrations on the trailing edge to minimize noise generation, or even the shape of the wing. So the sweep, so the angle changing on the front edge can also affect that. So there's all sorts of ways we can look at solving that very practical problem, looking at natural organisms.
Fantastic. Jim?
I guess it's very similar, I guess, to what I might have mentioned before. The envelope or the systems of a building need to we're constantly worried about energy and the use of energy and minimizing the use of energy, and ultimately using the environment to give us energy back through geothermal or solar power generation, using the energy that's consumed by a building, absorbed by a building, instead of just trying to get rid of it all the time. Like, these are the sort of the principles that we're struggling with every day. Using green walls, green roofs, all these sorts of things to sort of absorb energy and use the energy to grow greenery or foliage on top of buildings. Perhaps also encourage there's been a sort of a big push in Calgary the last couple of years for bees. How can we encourage bee populations, colonies to exist downtown on buildings? And I'm not sure that this experiment was very successful, but the ideas are very valid that we can use buildings to encourage growth as opposed to just destroying it.
Yeah, and when we think of bees, we think honeybees. Those are not native to Alberta, right? Alberta has huge amounts of solitary bees, and they don't look at all like bees. I highly recommend that you look up Alberta's bees. There's a fantastic project on biodiversity.ucalgary.ca with all sorts of recommendations on how to improve those solitary bee populations because they, right, pollinate our flowers and make sure that we have flowers in the summer. So, Linda.
Yeah, I think thinking of where we are in 2023 and the planet being the climate crisis being in immediate need of attention. Fire and flood is an important thing to me. I actually live in a little mountain town not far from here in Kimberley, BC, and the idea of fire has become potentially much more real for me, right, versus within a big city center. But we're just hearing, and you've probably heard on a flood situation on the east coast of the United States, they're bringing back the beavers to, especially in like the Chesapeake Bay areas, to do what they were naturally meant to do and to come in and reorchestrate the landscape so that the water moves and changes differently and bring back that marshlands. That I think is just, anytime I hear about that, they were parachuting beavers, I believe, into the Oregon forest, and I just can't figure out how they parachute them in yet. I'll have to Google that a little bit more.
I love that visual.
Yeah, I know. Can you imagine? Yeah. But the idea of fire, as I'm leading into that a little bit more, there's I just found this out, so it's very, very exciting. There's something called a fire chaser beetle, and this beetle, the firefighters have noticed that once the fire is somewhat extinguished, number one, they can sense fire over 80 kilometers away because they're actually going to go into the fire to look at, or they want to lay their eggs in burning or smoldering logs. And all our biomimicry passions, you start thinking, like, what's on their feet that can protect them, or on their back that can protect them from fire? So those are a couple ideas. So I should have qualified in my intro. So I'm not a biologist, scientist, or an engineer, but I just love the big thinking ideas and having all these great people make it work.
That's totally fine.
Yeah.
Anyways, I thought I was up early, but Kimberly, right? Like.
Yeah, I didn't drive in today.
No, I know. Still, yeah, and something that Linda brought up, right? We've sort of gotten used in our sort of built environment that we think that hard edges are going to stop water. We've now found out, right, that doesn't always work. And so things like bringing back mangroves, bringing back oyster reefs or mussel reefs, yeah. Right? Not only do those things slow down any water that might be coming in to shore, but they also filter water, right? So we have this sort of filtration system, a system that slows water down. So we have to kind of go back to those almost kind of vernacular practices in a way. Let me see. I'm going to go to the question of how is biomimicry used in industry, design, architecture, mechanical engineering. So that's going to be a variation on the previous question, but other examples of how it is used and maybe the difficulties in applying and using it.
Start with me.
Sure. You look keen, so yeah.
I'm pretty keen. It's an interesting question, I guess, internally, inside a building. What are we trying to do to mimic the environment? It's a challenge. Once you have a condition inside a building, it's very hard to change, and people are very particular, and they demand immediate action, and so biological systems tend not to be super fast in this type of context. So the key to this is to keep the conditions within a certain range and acceptable parameters to begin with, and using different types of systems we can use different types of energy, green energy, self-sustaining systems inside buildings or below is really the important part about this. Sensors, the challenges is control and economics. Honestly, at the end of the day, that's a very important factor. We can do anything, but it is expensive. It can be expensive. So the idea of finding reasonable solutions to these conditions that are affordable for the private sector as well as the public sector is actually key to doing this reasonably. So sensors is a big part of it, collecting data, and it's getting much easier with the Internet of Things to connect everything together. And cloud-based building management systems are really helping. We need to be able to control things real time and so that things don't get out of whack in any sort of extreme way, and be able to monitor and address conditions inside quickly and efficiently. So, inside a building, this is a very large space. It takes a lot of energy to manage and control this. So it is. It's a challenge, and so you need multiple zones, you need each sensor, you need each VAV box or air conditioning system to be controlled locally around windows as in the exterior of a building instead of the interior of the building. And all of these things, unfortunately, cost money. So I don't want to bring it always back to money, but it is a very important factor in how these decisions get made. But the good news is, I think that systems like this, data, control systems, mechanical systems, lighting, all of these things are getting cheaper to control and to operate. So this is the good news. I don't think we're there yet in terms of being able to do this efficiently, but it is changing every year. So that's the good news.
And that's the message that I give my students, right? Not everything has been invented yet. There's lots for you to do. So, Eric.
Sure. So when we're looking, maybe I'll answer this slightly more from the academic side, which obviously eventually is intended to have industrial application. But there's two ways we could mimic nature. One is directly mimicking form. The other is mimicking function. And sometimes one or the other might be more appropriate. Maybe more on the biophilic side, we're looking at very much mimicking forms for the aesthetic appeal. Myself as an engineer, I'm more interested in the functional side. And so when you mimic nature functionally, in the end, it may or may not even look like the original inspiration. The form may change depending on how you are changing, how your goals differ slightly than nature's goals. So one example, again, I'll go back to the Samara seeds, that when we see how that seed falls, the first impression is, well, maybe we should just make a wing that has the same shape, this sort of curvilinear borders that those seeds tend to have. And I've seen many projects looking to just mimic that exact shape and then throw it on a miniature helicopter and think that we've done biomimicry. But in fact, it's more important to look at aerodynamically, what is that seed doing? What is the flow pattern that it's generating? And in what practical purposes for ourselves will we find that same function useful? So that, I think, is an important distinction to make between form mimicry versus function.
Yeah, I always tell my students, right, bunny slippers are not biomimicry, right? They look like bunnies and are soft like bunnies, but tell us nothing about, right, the countercurrent blood flow, for instance, in the ears that helps it to cool its body temperature, right? So bunny slippers, no. Countercurrent abstraction, yes, right? So anyways, Linda.
Yeah, maybe from a very high level and speaking to both the philosophies that, does anybody know a incredible lady named Suzanne Smard? She's a forest and tree expert. She's out of British Columbia. If you get a chance, YouTube her. She's got a great TED Talk and some beautiful books out. But she speaks to something called the wood wide web, and it's how trees speak together, and it's all driven and controlled by the mycelium in the ground. So the funguses talk to one another, and then the trees talk to one another through the roots. I'm doing it like very simple, right? But to the point that we're saying from a biomimicry function perspective, the trees will even self-select one another. They'll tell one another that you're not going to get as much water over here, but you're going to get some water over here. And certain species of trees will speak to one another, and other species, they won't talk to one another, which is kind of like real world here. But this is all done without power, without electricity, without internet. So how can we lean into our building systems? We know architecture and our built environment is a huge component to to the planet and the situation we're in right now. How can we do it different and lean into all this great engineering and ideas out there?
All right, thank you, Linda. So we're going to move to questions from the audience and from our web audience. So microphones are moving around. Yes.
Hello. Wow, that's loud.
Hi, Kim.
Hi, how's it going? A question I would have is, I'm wondering if you have any examples where attempts at biomimicry have gone wrong and what we can learn from those.
It's not so much wrong and again, high level. So if you guys know this example of, so in Africa, they were looking at, brilliant architect was looking at termite hills and how they self-cool. And they, I understand they created these vents throughout the building to very much act like the draw of air when the air heats up and then the heat escapes. And I think it was a really good try. I don't know if it was 100% successful, but it was so encouraging to see, you know, the technology of anthills and how they cool themselves and termites. So that's one example I know of.
Yeah, that example was always presented as inspired by termite mounds. This is a building in Zimbabwe, in Harare, the Eastgate building. Biologists have debunked kind of the functional parallels and said, well, so, I mean, it was a nice idea. The building does save 80% of energy compared to other buildings adjacent. So they've done some very ingenuitive engineering, but the termite mount hill parallel is not correct. There's a company called Mirasol that worked on a structural screen for computers. That was developed. There were prototypes made. People were able to see their screens outside very easily, right? Sometimes with a laptop in the sun is very difficult. So this was sort of an outdoor screen. But it wasn't viable. People were interested in other things, and so they had to abandon the development of that. So that's one I know of.
One great example that I can think of related to this is thermal siphons in the north it's a type of building foundation where you drill a pile and you run cooling loops through the pile so that the pile does not melt the permafrost. So this sounds like a great idea, and it does work when the systems work. But the trouble with a lot of things like this is they're mechanical, and they require expertise and knowledge and maintenance and proper use for them to be effective. And unfortunately, the majority of these systems fail in short order because they're not maintained properly. And generally speaking, the failures, I think that's a good example of technology that's applied in a way that it's not helpful in communities where they don't have the ability to maintain, operate, or really understand the technology that they have in these buildings. Excuse me. So we need to apply technology in a way that is understandable and effective in the local communities for the people that need to use these systems. And to me, that's where things start going wrong, when we introduce things that people just don't understand and know how to use properly.
I can also finish off the example I brought up in my last answer about the Samara-inspired helicopters, of why I wouldn't say that's a failure, but it's something that hasn't necessarily caught on. When we're designing small drones, we don't automatically do Samara-shaped blades, and why is that? And I think the failure, if there is one there, is to not see how the goals of those two systems are different, right? So in a helicopter, we're trying to put energy into the flow to generate lift, and we need to do so as efficiently as possible. A Samara is actually doing exactly the opposite. As it's falling, it has gravitational potential energy that it's trying to get rid of to get to the ground, but it's trying to waste that energy as much as possible at the slowest speed possible. So in some sense, we look at them superficially and say, oh, these are both spinning wing systems, therefore surely we can learn from one and apply it to the other. It doesn't necessarily fail, it it's not necessarily optimal. So we have to always look at what are nature's goals and what are our goals, and are they the same? Because that's where the inspiration will be the most effective.
Joe.
Question from the online, again, just a little reminder, ssemc@ucalgary.ca for those who are watching online. The question comes in from Belen, who says, how is solar panel technology evolving to use the energy in place as it's generated during the day instead of sending it to the grid?
I guess I'll start with that one.
Yeah.
How is it evolving? Well, it's evolving very quickly. The efficiency of the panels is improving. The cost of producing the panels is going down, and it's becoming very cost-effective to in the open market in order to produce your own energy. The trouble is, it's not energy dense enough currently to really make an impactful difference. And that's, I guess, maybe that's my opinion coming through. But plastering a building with solar panels works, and you can do it, and it's very helpful to generate its own energy. But currently, buildings still need more energy than what a solar panel can create. So the other problem, of course, is that when it's dark outside, they don't generate energy. And so what is coming along very quickly is the battery storage technology, whether that's so typically literally a battery that you can charge during the day, so you have energy when it's dark outside. And combining those two things together is really what is starting to happen more and more. And the economics, therefore, of solar are really improving as battery technology improves. So it's going to become more and more important as part of a decentralized energy system. And I'm a big promoter of a decentralized energy model for any community. I'd rather go off a tangent on that. So it's changing a lot. Battery technology and combined with solar is really going to change things dramatically for every building.
Yeah, in terms of a biomimetic angle, there are all sorts of coatings being developed so that there's no ice buildup on solar panels, right? So to keep them clear so that the sun can hit the parts that are necessary. That was also something that was happening at NASA Glen, right? To the de-icing of vehicles is a big issue, right? Keeping dirt off of Mars landers, for instance, is a big issue. So how do you create surfaces where dust and ice and things like that do not adhere and interrupt what you're trying to do? So,
just in terms of the solar panels and snow, it is an improving technology. But what I saw just last week, or when it was snowing last, was an ice dam. So the ice and snow slips off of the solar panels very well, but then it hits the roof and it sticks and creates other problems that have to be considered. So the whole integrated solution there needs to be thought through a little bit more.
Yeah. So then Samara seeds are not such an issue, That's right. Much smaller issue. Yes, right. I see a question in the back.
So just a thought, if you think about how plants absorb sunlight and then convert it into, through photosynthesis to do things, are there any mimicry there that has promise for either gathering energy, solar energy, or making more use out of it more efficiently?
Anybody?
Not sure how to answer that one.
Yeah. I know there's attempts being made to mimic that, right? To find a parallel system that mimics that. Not super efficient, as far as I know. I recently saw an experiment slightly parallel, but a robot that would potentially be able to take regolith on other planets to generate its own oxygen and start generating compounds that we might need to grow things in other places. But in terms of mimicking, plants, I would say let's keep them in the ground and let them do their job. They do it really well. So I think, we have to remember that nature is this integrated kind of distributed system, right? It's very difficult to say, well, take this particular part from a natural system and mimic that, right? It's connected to so many other interacting systems. So let's keep our ecosystems going. Our ecosystem services, right, give us, I think it's now 125 trillion in terms of contributions. And that's just by purifying the air and providing us with oxygen and all this stuff. So I think preserving ecosystems and making space for nature is one of the best things we can do, probably.
Maybe I can just add, it's not an area I know a lot about. I remember looking it up out of curiosity. So I think artificial photosynthesis is an area of research. It would be more, I mean, it's outside of my area. It'd be more if we had a chemist up here, could maybe talk about that, of trying to mimic the chemical processes that allow plants to capture more of the energy coming in than our current solar panels do. So yeah, it is something people certainly are trying to mimic, but I don't know any more about it.
Yeah.
All right, another one from the online. This one from Kathleen. I find the connection between engineering, biology, and art to be quite fascinating. Can you help me and those in the audience understand what might be next in developing that connection?
No. Well, I teach a biomimicry course and an art and engineering course, so maybe there's a few things happening there. I hope to be surprised one day by a former student. I think, I mean, I've worked in engineering for the past 20 years, and I think engineering is an art as well, right? I think we've separated those things out too much. To create something that functions efficiently and elegantly is an art to me. And I think, giving engineering some education around elements of art and principles of design is very helpful, right? To sort of see the bigger picture in terms of how can I make this both super efficient, functional, and aesthetic at the same time. And I think nature can teach us a lot about aesthetics as well, right? We're automatically drawn to things in nature, right? We automatically kind of are happier in nature, right? Breathing fresh air, seeing plants, flowers, etc. So I think pull those things in. Don't see them as something separate, right? It's all part of the same thing.
Here's an incredible engineer. Her name is Neri Oxman. Have a Google of that person. She marries art and science and extreme boundaries of structure, pushing and pulling, all while being very connected with a natural response. So she's very inspirational. So have a check on that.
I have to put a plug in for Beakerhead as well. Beakerhead is based in Calgary. It's an organization that's it's a smash up of art, science, and engineering. I find that group very fascinating. It's engineers are notoriously, or from a reputational perspective, not good communicators. We like things to be black and white. We like it to be numbers. We like it to be answer certain, where there's no ambiguity. But in art, science, and engineering, bringing those three together means that people appreciate the fact that things are very uncertain and not necessarily clear, and people think in different ways, and there's a probability of solutions and the uncertainty of solutions that makes engineers feel very uncomfortable. And we all it boils down to communication at the end of the day, and being able to communicate ideas. People think differently. They have different priorities, and they're trying to achieve different outcomes. And it's a bit cliche, but that really does, in my opinion, boil down to everybody being able to communicate.
I'll add to that I do think we treat aesthetics as an afterthought sometimes in engineering. So if we're thinking very practically, we think about how to get that function, then only after think of, how can we also make it pretty? And you just put paint on the outside and think that's enough. But I think even starting from an engineering education perspective, or we're defining design requirements for a design project, It's one of those things where when the students have to put aesthetics in their project, it's like, ugh, like that's so subjective. How do I deal with that? But of course, if you had a solution to all the world's problems, but it were ugly, it would be rejected. So we certainly need to think about it from the get-go.
And we're seeing such an integrated approach as we sit at the table now when we're designing. Who thought that we could, architects and designers and engineers, and we bring biologists in now and chemists, and we'll bring experts in, and we'll bring, from an aesthetic or a human perspective. And this is really encouraging because there was, not that long ago, we operated in silos, and to see really quickly, even in the last 20 years, that we come together for the solutions. And to sit here thinking that we want to bring in nature into our solutions, it's pretty exciting times for us.
Good morning. I'm thinking about an earlier statement that was made about us as consumers wanting, for instance, the interior conditions of a building to change like instantly, changing our thermostat and having it, the interior conditions change really quickly. And so that got me thinking about sort of our role as consumers. And I was thinking about how, I guess ideally, we'd love for the world as we know it to simply, and all the systems that we know to be simply replaced by more efficient, more sustainable, and biomimetic designs, but perhaps that won't be how it is. We might have to adjust our expectations and our habits as consumers and as systems thinkers for what we consume and what we expect in terms of resource management and flow. So I guess my question is, what is our role for all of us as consumers and for those of us who are systems thinkers of what we might need to change about what we expect and anticipate and want from the systems that we have in place currently?
Maybe I'll start by observing if we're mimicking nature. Nature does move slowly, so I think you're right in pointing out sometimes when we want change to happen immediately, there's a cost always to that. Maybe an example, not so much biomimetic, but I've always been an advocate of using old cars. I drove here in a 2002 Civic, and to me, it's a matter of, sure, you could buy a new car every year that's slightly more efficient than the last and think that that's the way to go. But what about all the energy that goes into making that new thing, whatever it happens to be, a car, a phone, whatever it is? So I think being more patient with change is certainly advisable.
Yeah, I think globally, right, we have to consume less, use less, drive less, right? I mean, it has to go hand in hand. We can't, I think, maintain, right, what we are currently trying to do. So I think we have to scale back, especially in the West, right, because we are a burden on the global South. And so I think that's definitely something that has to go hand in hand with all these innovations. Is not to keep growing, but find the sweet spot.
That's a really great comment, because we have to ask. We have to demand more as consumers as well. We have to question, and we have to lean in. Well, I don't have to, but it'd be a good idea. Lean into inconvenience, right? Because having less could be inconvenient for a while until we shift our expectations and our priorities, so that we can with our climate crisis, just kind of shift a bit differently.
I'll just add one other thing about this. It's public policy, and as consumers and the public, we all have an ability to advocate, talk to our politicians, tell our politicians what we think are priorities for us, and as sustainably minded people and concerned for the environment, it's really important that we advocate for that in our communities and make sure that people are aware of the opportunities, the challenges, the problems that we need to address, and make sure that our politicians are paying attention as best we can. It's not an easy thing to do, but keeping the awareness in the public forum, I think, is really critical as consumers to make sure that we can tell people we don't want disposable coffee cups anymore. There's no need to do this. We have a way of producing compostable coffee cups, or using reusable ones is ultimately even better. So public policy is a big part of this, and as consumers, we can influence the policies that we set in our local communities, but also nationally and globally.
So that concludes our session. I would like to maybe give Eric, Linda, and Jim a round of applause for their contributions.
So let me echo that, Marianne, Eric, Linda, and Jim. That was fantastic. What a great discussion. I know our panelists, for those that are in person, are not planning on running away. And so if you had more questions that we didn't have the opportunity to get to, please feel free to come up and ask them. And for those online, Google is wonderful. Google them, find their email addresses, and I'm sure they would be very happy to have some follow-up conversations. Thank you, everybody in person today, as well as those that took part in our discussion online. And a welcome. Our next panel will be looking at future energy solutions, and that will be taking place in February. And so from now until then, I hope everybody has opportunity for some holidays, relaxation time, and for those locally, not too much snow, but just enough that we can still go skiing. Take care. Have a wonderful day.
Thanks for tuning in to this Schulich Connects, proudly sponsored by TD Insurance. We'll see you next time.